Thanks for coming, everyone. I'm Doug. I'm going to talk about, this library I wrote called Quadrable. I'm going to, discuss in a lot more detail how the actual implementation works and the data structure works itself. And then I'm going to get into a little bit about the underlying implementation and how you'd use it, for example, from C++ or as a user. But what Quadrable is an authenticated database. And what that means is that if I have a copy of a database and you don't have that database, how can you perform queries on it? And how can I satisfy those queries in a trustworthy way, right? So you know that I haven't actually tampered with them. I haven't manipulated them in some way, okay? The underlying data structure that implements this is a Merkle tree. We'll talk about that. And there are quite a few implementations of it. But one of the things that I wanted to do with Quadrable is make it sort of like something that I would want to use myself and like make it quite a bit flexible. Kind of Git is my sort of model for this. I want it a little bit more decentralized. There's a fairly close competitor, like one of the closer competitors I would say is Google Trillion. And it's a very difficult to set up system. You need MySQL and you need to write special adapter codes and things like that. I wanted something a lot more simple. Also with a command line tool just for experimenting with it. As I said, we're going to begin by talking about the underlying data structure of the Quadrable implements. And then also how a couple of the innovations, for example, in proof encoding that Quadrable uses. And then finally, we're going to actually talk about how to use Quadrable itself. So let's begin by talking about Merkle trees. So this is one of the, I would say, foundational data structures of distributed systems and also cryptography. And in fact, it was originally formulated as a cryptographic primitive to implement digital signatures. But nowadays, it's used for many other things. So you've probably seen it or seen things like it because there's many variations as well in some of these applications, right? Like Git arguably is a Merkle tree itself, as I'll talk about. BitTorrent, ZFS, many different database systems. Pretty much every cryptocurrency uses Merkle trees in some level. Even the notion of a blockchain is arguably a Merkle tree. And then another very interesting application called certificate transparency, which I'll talk about in a second as well. And as I said, the original application of Merkle trees was as a digital signature primitive, and that's kind of come full circle, right? Because now we're starting to be a little bit concerned about some other cryptographic primitives, and maybe Merkle trees will come and save the day, right? Just as a little motivational example, I want to talk about certificate transparency. It's this very interesting and, in my opinion, important project that tries to bring some kind of like accountability to the certificate authorities. Those are the entities that actually issue SSL certificates. The problem is that there's many of them, and they can, pretty much issue a certificate for any domain anytime they want, right? So Google was unhappy with this status quo, so they made this project where all certificates that get created by any CA get entered into this massive database, okay? That way, and browsers won't accept it unless they know it's part of this database, right? And that way, if a CA misbehaves and issues like incorrect certificate for google.com, let's say, then at least it's logged and there's evidence in this indisputable database called the certificate transparency database that they did that, right? The problem is, though, that this database is large, right? Every domain on the internet pretty much is going to have an SSL certificate now. How do you prove to a browser, from a potentially untrusted server, how do you prove that this was logged, this was added to this transparency database? This is an application of Merkle trees, okay? Another example that probably everyone here is familiar with is Git, right? If anytime you've run git log or looked at the output of many Git commands, you'll see these hashes at the bottom, right? Those are what they call commit hashes or commit IDs. And essentially what they are is just a cryptographic hash of the latest commit in the repository, right? And every commit embeds the hash of the previous commit. So if you rely on some of the cryptographic collision-resistant properties of a blockchain, what that means is that there is one unique history that results in this hash, okay? And any changes at all to that history will result in a new hash, okay? And it's computationally infeasible to find any different history that has the same hash. So what you could think of one of the terms that people use for these hashes is a root of trust, right? It's something that digests that entire history, right? And if you have that root of trust, you have that hash, then you can actually, given the content, reproduce it, and therefore be able to know for sure that the content is valid, is correct, okay? So example here, if you know that commit hash, is you got it from some trusted source, for example, you can download that repository from anywhere, reproduce the hash yourself, and make sure that no one inserted some bad commits into it or anything like that, okay? That's called tamper-resistant property, right? But the real kicker is where do you get that hash, right? Where do you actually get that commit hash to verify it from, right? Well, there's many ways that make sense to transmit a small root to someone versus a much larger data set. And just as a couple examples, you can transfer the hashes themselves out of band, right? So I could directly email you or instant message you the hash, for example. Or it could be like broadcast through some mechanism like radio, satellite, Twitter, and any kind of other what they call out of band mechanism, right? As opposed to in band, where it would be like along with the data itself, right? So some kind of trusted channel. And then of course, it makes sense to sign. It makes sense to sign commit hashes as well. If you're like a trusted issuing authority, you can say this commit hash I've made sure is good. Here's my digital signature, and transmit that separately. And then that way you have this sort of out of band channel for it. Another interesting way to transmit roots of trust are in the newspaper. And in fact, if you look at New York Times every weekend edition, since I think like about sometime in the early 90s, there's been this one little section on one of the pages. I think it comes out once a week. And it is issued by this company called Surety. And essentially they're just a hash of all these documents and anything that they've certified or notarized essentially in that last week, okay? So if you go and buy a copy of the paper, you can actually transcribe that hash and then use that to essentially get information from the Surety database and reproduce it yourself, okay? And surprise, surprise, of course, they'll be using a Merkle tree for that, right? So just as like a little bit of a motivational starter for this data structure, I wanted to talk about hash chains, okay? If we just think about the very simplest possible usage of Git, where there is no merging or anything like that, we can think of it as like a linear history, right? You add a feature, you fix a bug, and each one you're adding a commit on top of this, right? So it essentially forms a reverse linked hash chain backwards in time, right? Because remember that every commit embeds the commit hash of the previous commit. So let's say you have a commit hash that you trust, right? You've acquired this commit hash somehow, and it's the latest commit hash. And then you want me to prove to you that this one particular commit exists in that history, right? Well, the only way to do this with this sort of hash chain is for me to provide you that commit and then all of the future commits, right? And that way you could take that commit, hash it yourself, and then take the next commit, verify that the hash matches that, take the next commit, verify the hash matches that until you get to the very end, and the final hash of that commit should match your trusted root, right? And if that all holds, then yes, that commit was for sure a part of that history, okay? You've propagated the trust through this root and verified it yourself from a portion of the data, right? Unfortunately, if this commit was a really long time ago, there could be a lot of commits that happened since then, right? So there must be some better way. Well, surprise, surprise, hash trees, right? This is the way to do this in a smarter way, so that you don't need to transfer the entire history. Okay. By the way, Merkle tree and hash tree are just different terms for it. Merkle is just named after the inventor, Ralph Merkle. But really, what they are is hash trees, so you can call them that interchangeably. In this particular picture, I've kind of summarized some of the different nodes in this tree and their roles. We'll go into more detail about exactly how these things function. But for now, just look at that red one, which is like the item to prove. That's kind of like the commit we want to demonstrate is actually in the repository, right? And then the green commit is that root, is that actual hash that we got from the newspaper or the satellite broadcast or whatever it is, right? And then there's some extra special ones called witnesses, which are illustrated as blue here, which are kind of summary information about nodes below them in the tree, okay? So we'll go into more detail about exactly what they are. But first of all, why are we using trees in the first place, right? Trees have this beautiful property of exponential growth. And of course, if you flip that over, it's logarithmic growth, right? So it depends on which angle you're looking at it from, if this exponential growth is beneficial or not, right? In particular with trees, if we want to minimize the tree depth, or like for a given tree depth, if we add another depth, that number of leaf nodes at the bottom of the tree grows exponentially, right? Every time we add a new, if it's a binary tree, every time we add a new level, we're doubling the number of leaves, right? So as you all know, 2 to the power of x grows very quickly, which is nice, right? And the flip side of that, of course, is logarithmic, right? As you add more and more leaves, you require a logarithmically increasing number of levels, which is desirable, right? Because logarithms grow very slow. That's why we use trees. One of the limitations of the standard way of describing Merkle trees, like the traditional way, is that they lay out these leaves in a sequence, and they have sort of an implicit order. And the position of that item you want to actually prove exists is sort of arbitrary, right? Depends on, for example, the insertion order, like whenever you happen to add it, right? In a lot of applications, it would be nice if there was a way to actually query this by some sort of key, right? Or like maintain it in a sorted order, for instance. The problem with the standard description of Merkle trees is that order would need to get reshuffled every time you wanted to insert something into the middle, right? Or you could always just insert it at the end, but then of course the actual location in the leaves is sort of arbitrary, right? And it's also path dependent, right? If you add them in different orders, then you'll have different trees, right? Which is sort of not necessarily the ideal, right? You might want some sort of like key value lookup for this instead of just an unordered set of data. One slight variation that people do on Merkle trees is this, which is what I call a key value Merkle tree. Okay, and this adds the special concept where some leaves are actually empty, quote unquote empty. They signify that nothing is there. Okay, and other ones, as you transition the tree, you actually get to an element, right? So something has been added there. That's the element. Okay. So what you often might like to do is have some sort of key, which is an arbitrary string, hash it, and then take the binary representation of that hash and then use that as the path down the tree, right? And whenever you want to insert something, there will be one particular element at the very bottom of that in the leaves that is going to store it, right? And no other spot, and no other key will land up there. Assuming a collision-resistant hash function, right? Obviously, I'm sure you all see where this is going. The problem with this is that the trees are going to get gigantic, right? If we have 256 levels of our tree, for example, we want to support 256-bit hash, which is the kind of the standard, then we're going to have a ridiculous number of leaves in this tree, right? So it's going to be completely unwieldy, right? So there must be some better solution than this than to actually store all of those leaves as empty, right? Well, yes, there is. The solution is what we call sparse Merkle trees. And the idea behind this is that conceptually, yes, we have empty leaves, but we don't go actually bother instantiating those. We don't actually store empty leaves in our database or anything like that. Instead, what you can do is, if you think at the very bottom level, if you have 2 empty leaves, they're going to have a particular hash. Let's call it A, okay? And then if you have another set of empty leaves, and pair them together, pair them together and hash that, concatenate them, hash that, you also get A, right? So every pair of empty leaves at the bottom of that tree is going to have the same parent hash, right? Well, may as well just cache that once, right? Cache that lower level once. So when you have 2 empty leaves at the very bottom, the next highest empty subtree has a particular hash, and that's common for all elements in that level. And exactly the same if you go up to the next level, and the next level, and the next level. So every particular subtree that is totally empty at the same level will have the same hash, right? And that's the kind of insight that it allows us to actually instantiate sparse Merkle trees. And the first time I read this was actually in the certificate transparency paper, this notion of the caching it like that and efficient implementation of sparse Merkle trees. Quadrable actually takes this a little tiny bit further. And due to how we do key encoding, which I'll explain, we can actually just use null bytes as every level of the hash that represents an empty tree without any loss of security. I'll go into that in a little bit in a second. But the nice thing is we're using this, what they call dynamic programming method, to optimize empty sparse trees. Okay, next problem. We have 256 levels for a key, right? So all that path all the way down the tree. And remember, most of them are empty. It's not a big deal. But the ones that aren't empty, to actually add something to the tree, we'll have to do 256 different hashes, right? Every single level is evolving of hashing the two child nodes to get the parent node, and then take its sibling, hash those, and get the next one up. 256 hashes is a little bit unreasonable. I mean, like maybe we could do quite a bit better, right? So the solution that Quadrable uses is actually to what I call collapse leaves, okay? So anytime you have a subtree and there's only one leaf that is non-empty in there, we bring that up to the very highest possible level and store the leaf there, right? So what that means is that, and then there's also branch nodes, right? And branch nodes exist when there are multiple entries below it in the subtree, yeah. What that means is that once we have a particular leaf, then only the number of branch levels up to there is the number of hashes that are actually required to reconstruct it, okay? And you can think of the degenerate example where there is only one element in the tree, then the entire tree is just going to be represented as one collapsed leaf, right? So what happens, let me just quickly talk about the leaf hashing, the leaf hashing scheme before I get into like how we actually modify these collapsed leaves trees. But whenever you want to insert an item into a Quadrable database, what happens is you hash the key, and then you hash the value, and then you concatenate those as well as a trailing null byte, right? So what that means is that you have 65 bytes, right? And then that is what you hash to get the hash of the actual leaf, right? Of the collapsed leaf, all right? And there's some subtleties about why that's a nice thing. One of them is for security. That 65 bytes is a domain separation between taking two different nodes that are 32 bytes and concatenating them and getting a 64, right? So any internal, two internal nodes in the tree, if you compute their parent hash, it'll always be computed as the result of 64 bytes of input, right? Whereas a leaf is always computed with 65 bytes, okay? And that's a fairly important security property. But if you're interested in, the dirty details of it, see the documentation, because I go into more detail there. And the other kind of like nice thing about this is that let's say you have very large keys, right? Well, what we can actually do because of this is in some of our proofs, we can transfer just the hash of the key, right? And that'll actually reduce it quite a bit further than if we needed to transfer the entire key for some operations I'll talk about in a second. But anyway, let's talk about how we actually work with these collapsed leaves trees, okay? For example, let's say that we want to insert a leaf, right? Well, whenever we go down the tree, we're going to find a leaf that sort of conflicts with it, right? As we're traversing it, we're going to find the location in the tree where this subtree used to contain only one item below it, like one non-empty leaf, but now it's going to have to contain two, right? So what we do with that is what we call split the leaf, add a branch, and then put those two collapsed leaves below it, okay? Yeah, that's what we call splitting a leaf, right? But the way that Quadrable works is that if those two leaves share any common prefix, then unfortunately we have to add some more branches, right? And some of those branches will have empty right or left sides, right? There are some Merkle and tree implementations that kind of have what they call collapsed branches. So there would be only like one intermediate node in that branch and sort of compress, sort of like a tri data structure, if you want to think about it like that. For Quadrable, I didn't implement that because most of the time the keys will be hashes anyway. So the tree will be fairly randomly distributed throughout the space anyway. So yes, this is a little bit of an inefficiency, but I don't think that much of a big deal in practice. At least I haven't seen it to be. There are some exceptions like adversarial input. Again, see the docs if you want to know that there are some security quantifications for exactly that, right? If you have someone who's deliberately trying to make a tree with a very, very long branch node, right? I estimate the cost for them to do that and so on. But anyway, the nice thing about this is that the implementation is very simple, right? All we have are branches and collapsed leaves. And there's no weird extension branches or something like that you'll see in other Merkle tree implementations. The one other slight subtlety of the collapsed leaves is that sometimes when you delete an element, you will actually have to propagate it further up the tree. Okay, take a look at this particular example. In this case, we have a tree with 2 elements in it, and they share the first 3 bits in common, right? And after that, they differ by the 4th bit. All right, and we want to delete now one of those items. Well, if we just went and deleted that red leaf at the very bottom on the right, then what we would get is sort of a tree that's violating our invariance. Okay, what would happen is that we would have a subtree where the leaf is not at the very top, right? When there's only one actual leaf below it. That's not what we want. So in order to do this, we have to actually what I call bubble this leaf back up to the top to preserve the invariant such that this leaf is at the highest possible level. Okay. And it was a little bit tricky to code this up with all the recursion and everything you need to do, but it's working now. So the great thing about all this is that we now have a path independent data structure, and what that means is that we can add, remove leaves in any order we want, like records, key value pairs, and at the very end of whatever we've done, we get a hash. We get the root of this tree, right? That doesn't reflect any of the history about which order you're adding or deleting things. It's purely about the actual records that have been inserted, their keys and values, right? So if you had different order, then it would still give you the exact same root hash, right? So it's purely a digest of what's actually in the tree, all right? As another way to put that is identical trees have identical roots, right? Like similarly, if you add something and then delete that, you'll get back to the root you started, and so on, right? Okay, proofs. So why are we doing all this hashing in the first place, right? Like this is if it wasn't for what I'm going to explain now, then we may as well just use a regular tree, right? There was not really any benefit to doing all this hashing of nodes and using that to figure out the next level and hashing those and so on. So the reason why we're doing this is that, as I said, this is an authenticated data structure. So we want to be able to prove that elements exist or do not exist. That's called non-inclusion to somebody else who only knows the root hash, okay? So if somebody knows the root hash of a tree and nothing else, and we should be able to send them some information that says, this element is in the database. And they shouldn't have to trust us at all. They should be able to recompute totally that, yes, nothing was tampered with. This is a valid record in the database, and there was no way of, sneaking something in or pretending something doesn't exist when it does, and so forth, right? So to actually support that, that's where the witnesses come in. Okay, witnesses are sort of nodes or summaries of nodes that are sent along to a verifier purely so that they can verify the proof. They can verify this element that they do care about exists in the tree or does not exist, right? And they don't actually care about anything else from the witness, right? So it's just a portion of the proof. And I'll talk about exactly what that means now. So hopefully you can see this example tree here, but this is sort of like you could call it like a simulation about what we're going to do with a proof. Okay, you see on the left we have the full data set, which is this potentially very large Merkle tree, and there's the root node at the very top, which is the trusted root. That's why it's green. And then there's the red node, which is the node that the remote user wants to verify, right? They're interested in this. So they ask the server, which has the full data set, I'm interested in this red value. Can you please prove it to me or that it exists or does not exist, right? And by the way, I know the root hash is this green one, okay? So what the remote user does is because they know the key of what they're querying for, they actually know the path through this tree, right? They don't know where it ends yet, but they know the path all the way down, right? They don't know when it's going to get collapsed, but let's just say for the sake of example, they drew it all the way down and they've plotted it here, okay? So that's where we land. The first thing that the server does is take that red node, that one that they see in the database, and then perform the hashing of the leaf value, and then they take the sibling hash, and then they concatenate those, and then hash the combination, and that gives them the yellow element. Okay, and that's what we call an intermediate node, right? And by the way, that sibling node is going to be required by the verifier, so that's what we call a witness. All right. So that yellow node is not part of the proof that it needs to be sent because the verifier obviously can just compute it, right? The verifier is going to have the red node, which will be sent by the server, right? And then they'll also have the blue node, which will be the witness. That'll be sent along with the proof. So the proof verifier hashes those together and recomputes exactly what the server is doing and so forth. And then that continues all the way up the tree, okay? So the server says, okay, now that I've computed that first yellow node on the bottom, I need another witness, so I'm going to include that with the proof, and then hashes them together, and then says, okay, now we need another witness at the next level, and finally we need another witness at the top level, or like the second level, depending how you look at it. So what the proof actually is those blue nodes, right? The proof is those witness nodes. And then the red node is sent along with it as well. And then what the verifier does is just combine them, but as you can see in their sort of simulated version of the tree, and then verifies that that final hash matches the trusted root hash, right? The green one, okay? So if all that checks out and the top yellow one matches the green one, then they know they can rely on that red one being in the position that the server claims and also hasn't been modified in any way, yeah. So that's the simplest kind of way that a proof works, right? Just sent along these witnesses and they're hashed together like in order of the key, right? Because you need to know which one is on the left and which one is the right. Well, that just corresponds to the bit in the hash key representation, right? So one of the kind of innovations, I mean, I'm not claiming I invented this, but one of the things that is a little bit novel that Quadrable does is it actually can combine multiple proofs, right? So if you know, if you want to query 2 elements in the database, for example, so a lot of that, like the simplest possible thing to do would just be to get 2 separate proofs, exactly as we described previously, right? And that's what you can see here, right? You have 2 sibling nodes, you're interested in querying both of them. So you can ask the server and they'll give you 2 separate proofs, each of which would be 4 witnesses, right? However, that's a little bit redundant in some ways because as you see at the top, some of those witnesses are the same in both trees, right? They're just both the exact same node in the same position of the same tree, so they'll have the same hash, right? So why are you sending them along twice? It doesn't make sense. It's inefficient. And then the other one is a little bit more subtle, the computable ones, but you'll see that in some of the elements are yellow in one proof, which means that they were computed, right? They were actually hashed together by the user, so they didn't need to get transmitted along with the proof. Whereas they are witnesses in the other one, right? So in fact, if you kind of think about combining these trees, these 2 proofs, that some of those blue nodes will disappear, and I'll show you that combination here. Okay, so this is the combined proof, right? You see that in the previous one where some of them were blue on one side and yellow on the other side, well, we don't need to send those witnesses along. We can just use the yellow one from the other proof. I'll just back up a second so you can see again. But yeah, you see, at the second from the bottom level, you have 2 witnesses there. Whereas here, once you've combined these proofs, you have no witnesses, right? So rather than needing 8 witnesses total, that's here, to prove 2 elements, we've compressed that down to only needing 4 witnesses, right? This is most beneficial when you have nodes that are close by. In other words, they share quite a bit of a common prefix. But in fact, you get a pretty good improvement in reducing proof sizes in a lot of cases. The other kind of semi-innovation in Quadrable is how I do the proof encoding, okay? A lot of Merkle trees implementations, they just give you a list of witnesses, and that's it, right? It's fairly difficult to implement this combined proof technology, this combined proof optimization. So what Quadrable uses is this, what I call a command-based proof encoding. So it's sort of like your proofs actually are these little mini programs that the verifier is going to run to reconstruct the tree, right? The way that I can conceptualize the algorithm is that you have these different strands, which are like little balls of yarn that you're going to kind of start unwinding up the tree to get to the very top, okay? And essentially what you do is you merge them together until you end up with just one strand, and then you're done, okay? So that's very wishy-washy explanation. I'm going to try to walk you through a quick example to hopefully make it more concrete. But in this case, we have 3 strands we're starting out with, okay? 0, 1, and 2, okay? Strands are always listed, in numeric increasing order like that. And the strands themselves contain the leaf data that you're interested in proving, right? That are actually included in the proof. So here I've drawn them out as 3 little red nodes, which are ones that the verifier is interested in learning about and making sure that they're authentic. So the very first command, I should say, these little programs are stateful, right? So they kind of, they jump around between different strands. That's what the red arrow is referring to. The algorithm always starts with the arrow pointing at the last strand, right? And then we'll see what happens when you can jump around between strands as well. So here it's pointing at strand number 2. The very first command is to hash with this particular embedded hash. That's part of the program, okay? So let's see what happens to the trees after we do that. Or well, the tree on the right is being constructed, and those are the strands in the proof. Hash, and what happens is we take that hash, which was the blue node, and combine it together with the value that was in the strand, and then we get the intermediate node, which is the yellow one. And I haven't drawn this perfectly, but the number 2 strand moved up, right? You can see it jumping up. And that's because it goes up 1 level higher, okay? And then the next thing we do is we hash with the empty hash, right? Which in memory quadrable is all zeros, all 0 bytes. And what that gives us is an intermediate node, which is a branch that doesn't have a neighbor, okay? And notice again that 2 is now moved up to the same level as the strand of 1, okay? So that's all well and good. We're recreating this little mini tree on the right. Remember, we're tracking this stuff as the program runs. But we're still pointing to number 2, right? What the program says now is jump to 1. So go ahead, and now the arrow moves to strand number 1. And the next command is another one we haven't seen. It's called merge. And what it does is it actually merges 2 different adjacent strands. It merges the current strand with the next strand on the right. And then essentially what it does is unlinks the strand on the right, okay? And it's no more, okay? However, if there was a strand number 3, that would now become strand number 2, you could think of it, okay? That's not how the implementation works. It actually keeps it as number 3, but it deletes it from a linked list, okay? But you can see the recreated tree on the right there. We've now added another intermediate node, merging one of those 2 strands that it represent, right? Remember, our ultimate goal is to get this into one tree. Okay, next command, we're gonna jump down to strand number 0. There we go, pointed at 0. Now this next command I just did to illustrate that we can actually combine hashes. Multiple hashes can be embedded, can combine into one command, which optimizes the proof encoding very slightly. So here we've actually embedded 2 different hashes that are going to bring it up 2 levels in the same command. Doot, right? Now we've gone up 2 levels. This leaves us with 2 final strands, 1 more merge, and we have the final tree. Okay. So now we've actually reproduced the portion of the tree represented by this proof, okay? And in Quadrable, what happens is you're actually storing this in your database. So this is not like just verifying the proof, but you're actually reconstructing the tree, right? That's why proof is almost like a weird thing here. It is the data itself. It's recreating this tree that is a subtree or a subset of the original large database, right? And that's why we call them partial trees, right? In Quadrable, there is really no such thing as like a, verifying a proof and then plucking the values out of it to use them. No, you just reconstruct the partial tree, okay? So after we do this, we have this partial tree, and the reason why it's a partial tree, of course, is not a complete tree, is because it has some blue nodes. Remember, those are witnesses. Those are nodes that we don't actually know the value of. They're just kind of summarizing some information below the tree, okay? And the cool thing is that we can actually perform lookups on this tree, right? So if we traverse this tree and look for a red element, it's perfectly fine, as long as we don't ever hit a blue node, right? So if we were looking up the right bottommost red node, as long as we traverse right, left, right, we'll never hit that one. And another interesting consequence of this is that we can actually modify those nodes, right? If we want to modify that red node, well, it's perfectly fine as long as we're not going to hit the blue node, right? We can always recompute those yellow nodes and create a new tree. And that would have been and then after modifying, we get a new root hash, of course, and that root hash would have been the same value as if we had the full database, right? So if the person who had the full database modifies the tree in the same modification as you do, you will get the same hash that they did, right? Yeah. So here is why I kind of like been, dancing around a little bit about like what witnesses are, but this is why they're cool, right? Is that blue node, there could be a giant tree under there, right? But here it's all just summarized, right? And this is why proofs can be so much smaller than the entire database, right? Every blue node can summarize an arbitrarily large tree underneath of it, okay? And another cool thing about partial trees is that if we have this partial database and we get a new proof, with Quadrable, you can actually merge this in and expand your tree, right? It can be growing over time. You get a proof for this one and a proof for that one, and a proof for that one. Sooner or later, you're going to have, the full database, or a much larger set of the database. Okay. Another cool thing you can do is if you have a partial tree, then you could now be considered like a server, and you could prove to somebody else, hey, well, I don't know the whole tree, but I can prove to you that this one element exists in there. So you can actually take like a sub-proof and send that off to somebody else, right? And you see here how you have changed that yellow element on the second level at the left from this tree that you partially know underneath it, and you summarize it just into a blue element for this new tree that you're exporting. Okay, so you give this new proof to whoever wants to query your mini database. Okay, so that's why I think it's so elegant to think about these things as partial trees and encoded partial trees rather than like proofs with data next to them, right? And then this is a little bit of just a tricky kind of detail, but how do you actually prove that a element doesn't exist? Okay, this is called non-inclusion proofs. If we were doing non-collapsed leaves, then it would be easy, right? Every leaf that doesn't have something there would be the special empty value. So we would just prove the inclusion of an empty value at that location in the tree, okay? Unfortunately, we can't do that with collapsed leaves because we don't actually instantiate empty nodes, right? So the proof encoder has to be a little bit smart. In order to prove that a key doesn't exist, what it has to do is create enough of a partial tree so that when someone does go to query it, they will see that the leaf doesn't exist, but will never hit a witness node. Okay, there's two ways of doing that. Either you hit a leaf that's blocking the path, right? Because you know that that's the only leaf under the subtree that exists, and there will be no other leaves under that subtree. Or you hit a branch that's empty on one side, and you know there's absolutely nothing under there. Yeah, so that's just a little bit of a trick. Okay. That's the data structure. So now you know everything about how Quadrable implements Merkle trees. I want to talk a little bit about how you would actually use this. Yeah, go ahead.
So I've been thinking about this in terms of CRGTs because I see some connections there. So if I have a partial replica of the tree over here, right? That's what your database of proofs that you've received so far.
Yep.
Becomes. Is there any way for me to incrementally update that replica when the source of truth changes?
Excellent question. Yes, there are some ways of doing it. There's one thing called what they call Merkle mountain ranges. Yeah, I know, it's a funny name. But actually, if I go back to the certificate transparency slide, they kind of allude to it a little bit here. You see that there's actually an old Merkle tree hash and a new Merkle tree hash there. The way that this works here is that you can still actually use some of those old roots for the partial tree. This doesn't work quite as well when you have the key value trees that I'm talking about. But there are some things we can actually do. For example, I haven't even mentioned these slides yet because it would confuse it a bit, but we can actually support like a log-based data structure like this in Quadrable as well. You can actually sort of rewind time to a previous version of this when the log was at this particular depth and recompute the Merkle hash from that. Come talk to me after, or check out the docs for this because there are some things we can do. But that is like one of the kind of like the biggest problems of this whole thing is that if the database changes, then your entire root is invalidated, right? Yeah. CRDTs are actually fascinating too. I think there probably is some synergy with Merkle trees, but I haven't thought about that enough. Yeah. Okay, usage. All right, thank you. So the moment you've all been waiting for, some C++. Quadrable, as its backing story, uses LMDB, which is actually a C library. But I maintain these bindings, C++ 17 bindings for LMDB. LMD is awesome in my opinion. It's this embedded key value database. So it's kind of like SQLite. It's embedded. It's not going over to a server or anything like that. All it does is open a memory map file, right? So and also there's no user space buffering whatsoever. All data is stored in the map. LMDB has full ACID transactions, excellent durability, excellent isolation, everything. And almost no tuning or maintenance is actually needed. It performs extremely well under a lot of workloads, especially read-heavy workloads. A little bit not as well under write because there's a single writer that locks the database at once. But you can often, get around that, or like you can often amortize multiple writes in single transactions and do other things like that. But reads are amazing, right? Because there's absolutely no locking whatsoever. It's just following pointers in the nmap. So you have 64 cores in your Linux machine. All of them can fully saturate reading from this database independently. Also, there's no write-ahead logs or anything like that. Crash recovery is instant. Startup is always instant. You can restart it, and all the page cache remains warm in exactly the same order of records you've read before. It's brilliant. C++, this is how you use Quadrable. You need a LMDB database, and then you create this Quadrable object, and then you do some initialization, like set up some of the tables inside of a write transaction, and then you're good, and then you're set up. Now you have a Quadrable DB. So here's how you might want to actually put some data into there, right? There's this put method on the DB, and by the way, everything needs to be done inside a transaction. Because that's LMDB. Every modification needs, or read has to happen inside of a transaction. So here's an example of inserting two records. Key 1, val 1, key 2, val 2. That works, but it's actually a little bit suboptimal, right? Because if you remember, every time we modify this tree, we're actually having to recreate a whole bunch of intermediate nodes and like do a bunch more hashing and all the way up the tree, and we'll get a new hash, right? If you do that 2 times independently like this, you'll be just throwing out those intermediate nodes you made from the first modification, right? So what Quadrable does is allows you to make this like change set object, and you can call put or delete on that change set object, and it'll buffer up those changes and then make them in one modification, which involves only one recursive traversal of the tree, okay? So that ends up saving quite a bit of like intermediate work, which also reduces the load on the garbage collector, which I'll talk about in a second. Reading is a little bit different, but also similar. With read, obviously you use a get method, the analog of put. It returns whether or not the element actually exists, right? And if the element does exist, it modifies that argument you pass by reference, the val argument, which is a string view, to point to the data itself, okay? This is great because it uses LMDB's mmap, right? So that string view is actually pointing into the memory map itself, right? Which is wonderful because there is no copying done, and there's also no memory allocation done for the read. So that's very nice. However, I have like very conflicting mixed feelings about how string view and how it works in terms of memory safety. But it's very useful, very efficient, but it's sometimes you can forget that this thing is actually pointing into the nmap, and then you like close the transaction and then try to use the string view again. Well, guess what? Someone could have gone and changed the database under there, right? So you have to be very, very diligent about the ownership of when you actually use this string view, right? So anyway, that's how it works. Of course, if that is a concern, you're making this mistake a lot, then you can just copy that into a string, right? And then it'll persist, obviously, when the transaction's done. Reads actually have a fairly similar property to writes in that if you do traverse the tree, if you want to look up multiple items, you'll have to traverse the tree multiple times, right? So you can actually batch reads as well with this get. You can actually pass it like a std set or something like that of strings, and it will look this up and do it one traversal. Oh, thanks. Yeah, I'm running a tiny bit over time, so I'll try to speed through this. But yeah, I say better maybe because like this isn't always necessarily better because now you're actually like doing std sets and things. So LMDB has such low overhead for a lookup. It's probably better just to not batch in most cases. Reads. Okay, QuadDB command line tool. I want this to be like Git. I want it decentralized. I want it, very lightweight. So I've got this command line tool. You just run it init on it, and it'll make you a QuadDB directory, which happens instantly. It's just initializing the LMDB databases. And then you can run quad-db status. And it'll start off just like Git on like your master branch with an empty root. Remember, empty root corresponds to empty trees at every level in Quadrable. So this is showing your current head, all right? It's kind of like a Git branch, but I didn't want to actually call them branches because that would be too confusing because we use branches for other things in this concept. But anyway, it shows you that. Here's how you would do put and get. You put key val and get, and it prints it out. There's all kinds of like bulk import methods, like import CSVs and stuff too, but like this is the most simple way to do it. And then let's say we do that and we go quad-db status, we'll see this new root that was created. And that one in parentheses on the right, that's just internal node ID. It's not that important, but it's useful if you're debugging this and things like that. Delete works the same way. You pass it the key, it deletes from the tree. And then because this is path-independent data structure, remember, we go back to the empty tree after we delete the element that we just added, okay? Okay, so all of those diagrams I did before are accurate, and they work in terms of the concept of Merkle tree, but they're a slight simplification of what we actually do at the database level. At the database level, we never actually like delete or modify a node. We only ever add new nodes that point potentially to the old nodes, right? This is called copy on write. It's if you're familiar with copy on write, like memory pages and all kinds of other things, you'll be familiar with it. But the reason why we do this is that it makes like creating new trees, like modifications and copies of them and so on, very, very cheap, right? In particular, like you can take a snapshot and start modifying it and have both trees at the same time, and that's a very inexpensive operation, okay? And fork is instantaneous. Fork is what I'll explain here. So if you go quad-db and you have an empty tree, you can check out this new head called temp and start modifying it, and then you can actually fork it to temp2, right? Now you have two temps, right? And they're both copies of each other, right? That last copy was instant because it didn't actually do anything. It just pointed both to the same tree, right? It's only when you start modifying it that it will actually start adding new nodes, but that would be very fast even on a very large database, right? Because of the beauty of logarithmic growth. All of those things you can also do on the C++ API. And then proofs, here's how you export them. You can just pass the sets of keys you're interested in proving. If you're also interested in proving that a key does not exist, you pass it there as well, right? And it'll create, as we said, that partial proof that the proof encoder makes it so that you can prove, for example, key 2 doesn't exist in this tree, right? And then similarly, you can decode the proof. And yeah, this is where the actual comparison to trusted root comes in, right? This is where you would pass the trusted root. And if it doesn't match, an exception is thrown. But if it does, you now have a partial database that you can use to do any kind of querying and all the other cool stuff we talked about. Garbage collection, copy and write, it's creating new nodes, and potentially you might want to get rid of them at some point. So it uses the standard mark sweep data collection as that, you're probably familiar with almost like Java and all these things do that. They, start from all the heads and mark all the nodes that they can reach and then delete everything else, okay? And LMDB lets us do this in a really awesome way with a read-only transaction that doesn't impact anything, da-da-da-da-da. Walk tree is this kind of like generic, I only put this in here because it's kind of a sort of neat use of C++ features, but it's this generic tree traversal mechanism, used for lots of stuff in Quadrable. Here, this is actually the implementation of mark tree, right? This you call mark tree on every head that's in the database, and it will, keep a record of all the nodes it finds, so that you can later delete the ones that it didn't find, right? So you pass it a lambda, and it gets a node, and you can do whatever you want with that. And I use this for all kinds of things like computing diffs between trees and DB stats and so on. Okay, very last thing. This is a work in progress, but I'm making this UI that's kind of like a spreadsheet. And at the top, instead of like a file name you have for your spreadsheet, I guess, you actually have the commit hash. And you can like highlight some of the rows and click export proof, and you'll get a little file, and you can send that to someone else, and they'll pull it up, and they'll get their own spreadsheet, which only contains those rows, and they can like make modifications, and it's going to be pretty awesome when it's done, if I ever get around to finishing it. Thank you very much for your attention. Right. So the question is, you have two different updates you're making at potentially in parallel, and you get two resulting trees, and you want to merge that into one tree that encompasses both results?
Yeah.
Yes, it's fairly easy. And in fact, the Quadrable has this diffing functionality, which will reduce it to the minimum set of modifications you need to turn one tree into another tree. So yeah, what you could do is start with that, either of the trees, and then diff it against the other, and then you would get the set of modifications to turn that tree into the other tree. So I guess you could diff both of them and then apply that to yeah, I guess actually you'd have to find sort of like they have a shared common history, I guess. So you'd be diffing against that, right? And finding all the modifications happen against that, and then replaying one of them onto the other tree. Yeah, yeah. I haven't done too much work into that, but that is something that does sound important.
In a key value setup, you can obviously have conflicts if you try and do that, right? Because you can have different values added for the same key. So what would you do about that?
So they just overwrite the old values. Yeah. So. True. Oh, yes. You're talking about in this particular algorithm. Yeah, that's a good point. Yeah. Well, yeah. Then you get into like merge resolution problems. Yeah. Yeah. This is yeah. You'd have to solve it somehow. And I guess like you're getting into like using a CRDT or something like that, and keeping like a version of each one or something. And yeah, it's a neat idea. Yeah. Yeah. Definitely, you have to handle merging somehow. Good point.
I wanted to get a bit more background. Like first, like. In terms of applications, what are you using Quadrable for versus everything else? Thank you.
You're welcome. So I first started making Quadrable with this idea that it would be for this thing that they call optimistic rollups on blockchains. And the idea behind that is that it would be nice if you could sort of make a whole bunch of modifications to some kind of database and then have to only put the smallest amount of information onto a blockchain, which is very expensive to actually store. So you could, you could have a very large database that most of it isn't stored on the blockchain, but only a small amount, only the root really needs to be, right? So I actually wrote a Solidity implementation, which is like a Ethereum smart contract language to decode Quadrable partial trees and actually make modifications of them, right? So you can imagine a smart contract has a particular root. Someone could pass in enough value so that the contract can prove that, yeah, this is part of the actual database, make some modifications to it, and store the new root, yeah. But that idea I had, other people were doing different things, and I never got around to finishing this. But yeah, I kind of have some like kind of generic, general purpose sort of plans for this. I don't know exactly what I want to do with it, but I feel like there's some pretty cool applications.
Awesome, thanks.
Welcome.